In recent years, many countries are focusing on distributed generation and microgrid because it is pollution free and flexible. Distribution generation in microgrid need all kinds of power electronic devices, especially inverter, to transform the DC source to three-phase AC source. These power electronic devices bring in considerable harmonic current. Meanwhile, there are reactive power loads in microgrid. More seriously, some distribution generation equipment also needs inductive reactive power. For example, wind turbines, which may lead to serious voltage fluctuation. These problems cause abnormal operation to sensitive equipment and make the power quality of microgrid unsatisfactory. Sometimes microgrid even can't work properly. Therefore, improving power quality of microgrid is a crucial problem. Remember two things here. To improve the power quality, we need to satisfy two main things. First one is harmonic current mitigation. So first of all, we need to eliminate the harmonic current, and also second thing is we need to compensate reactive power. So second thing is reactive power compensation. So if you do these two things, then our power quality will be automatically improved. Okay. So just remember these two things. Traditionally, we use power filters or static var compensator to improve the power quality of microgrid. These filters include active power filter and passive power filter. So here I already told you, to improve the power quality we need to satisfy two things. First one is mitigate the harmonic current and also compensate the reactive power. Okay. So if you coming to power filters, there are two types, right? Active power filter and passive power filter. So if you take active power filter, it mainly mitigates harmonic current and also it compensates some of reactive power. This method is much more adaptive and good at real-time application, but it is more expensive than the static var compensator in reactive power compensation. And when coming to the passive power filter, it can mitigate some of harmonic currents, but it is uncontrollable and also it has bad real-time performance. And when coming to static var compensator, it can mitigate some of harmonic currents and also it can compensate reactive power at a great amount, and also it can weaken the three-phase imbalance of the microgrid. That is other advantage. More importantly, it is cheap in reactive power compensation. However, it is uncontrollable in harmonic current mitigation. So by observing this comparison, we can find that active power filter or passive power filter or static var compensator performing alone cannot achieve satisfactory result because active power filter is good at harmonic current, static var compensator is good at reactive power, but we need both to improve the power quality. Okay, so that's why in our research we are proposing combination of active power filter and static var compensator to improve the power quality in microgrid. So by combining these two, we can take harmonic elimination advantage in APF and also reactive power compensation in static var compensator. And also if we install them at proper places, then we can improve the power quality in microgrid easily. In this new combined system, active power filter is placed at outside of distribution generation inverter. Considering equipment cost, here it is mainly mitigates the harmonic currents. And coming to static var compensator, it is set near at the load of microgrid. It mainly mitigates the harmonic of the load and compensates reactive power to the load. It keeps the voltage near the load stable and then reduce the power losses on the transmission lines. So this active power filter and static var compensator working together can improve the power quality of microgrid. Actually, the static var compensator comes under fact device. It is one of the shunt compensator device. Okay, it is always connected to parallel to the transmission line. That's why it is called as shunt compensator fact device. Okay, and if you see the static var compensator structure, it consists of thyristor controlled reactor TCR and also thyristor switched capacitor TSC and also some filters and control algorithm. This all comes under static var compensator. Okay, like this static var compensator, if you look into our block diagram, this is our distribution generation where generation is came. Okay, so it consists of DC. To convert the DC into AC, we are using this inverter. At the output, you will get the AC. Okay, and here to mitigate the harmonic currents and also improve the reactive power compensation, we are using these two filters APF and SVC, and we can give it to the loads and power system. This is our main diagram. Okay, but alone APF and SVC can't mitigate the voltage or compensate the reactive power. They need control systems and sensor elements to track the voltage and currents. That's why we are depending on the control system parts to detect the harmonic currents. So here we are using our control strategy is DQ control strategy. Why? Because we are having three-phase power system. First of all, we will convert this three-phase into two-phase, then control the parts by using PI controller, and again convert into ABC three-phase because systems need only three-phase. For controlling purpose only, we are converting that into two-phase like direct axis and quadrature axis. Again, after controlling, we can convert into three-phase system. And by using pulse width modulation, here we are using the space vector pulse width modulation and give that pulses to our switches of power electronic devices. So based on this control strategy only, our system will track the inputs and compensate the reactive power and eliminate the harmonic currents. Okay, now look into simulation diagram. So this is our simulation model. For understanding purpose, first of all, I am showing only with the shunt active power filter. Here we don't use the SVC, static var compensator is not using here. Okay, so it has the DC source here, and we are using the inverter to convert this DC into AC, and we are giving to the active power filter. Here it is connected in shunt parallelly, that's why we call it as a shunt active power filter. Then we can give it to the power system with the help of transformer and also with the help of some filter here. Okay, and below we are taking the load here. Now just run our simulation and look how we are having the output, whether it is good or having the harmonics. Okay, now just open the scope. Here just zoom it, you can able to see harmonic content here. So this waveform is not at all purely sinusoidal. It has pure sinusoidal, but it have a lot of harmonics. So here our active power filter can't able to control our system alone. Okay, so now I will show you the combination of static var compensator and also shunt active power filter. So now the same diagram, same concept with two components. One is active power filter and second one is static var compensator. Now let's see how it will perform. Just run the simulation, and now you can able to see the waveform here. Just zoom it. So here you can able to see it has less harmonic when compared to active power filter alone. Okay, you can able to see both waveforms. This is without SVC, that means only single. This is with SVC. You can able to see difference of that harmonic content here. Okay, by using both we have very less. By using only one device we are getting the more harmonic. That is the conclusion of our concept. By using active power filter and also static var compensator, we can improve the power quality in our microgrid. Okay, if you want this concept, just contact me. I will explain you more detail with control strategy and all. Thank you.